As you already mentioned, we didn't have a talk about batch normalization, but I actually, in my presentation, I explained briefly batch normalization. But I should also mention that this paper is inspired by batch normalization, which is a commonly used trick to improve the training of deep neural networks with the help of initialization. Actually, in this approach, we initialize units with normalized data. And this method follows two aims. First, to solve the common problem of vanishing and exploding gradients. And secondly, to speed up training process by optimizing the loss function. And I will explain it briefly, this approach. And I should say that there are some other approaches try to train the network with the help of normalized values, but batch normalization is actually one of the most successful ones. In this paper, they try to propose a new method to reduce the noise and regulating effects caused by batch normalization. As an introduction, first I start with the definition of this expression, weight normalization. Weight normalization is a reparameterization of the weight vectors in a neural network that decouples the length and the direction of the vectors. Well, this method is inspired by batch normalization, as I already said, in the way that it speeds up training of a neural network with stochastic gradient descent. But unlike batch normalization, it is a good choice for training recurrent neural networks and noise-sensitive applications. And also overhead composed by this model is lower than the models like batch normalization. Sorry. First, I give you a small recap of batch normalization because these two subjects are kind of tightly related together. So what batch normalization does is it takes a mini batch of data and it feeds it through the network, and in each step it takes the pre-activations. Then it computes the mean and standard deviation of all samples in a mini batch, and it normalizes the activations. As you can see here in the formulas. So it normalizes not even the first layer inputs, but also the values deep in some hidden layers in the neural network. And it is a very successful method for so many applications, but it has a property which might make it less suitable for some applications. Imagine training time. You just train the model with some limited samples of a mini batch. But if you test the model for the rest of the samples in a mini batch, you will see that it is also a function of the rest of the samples in the mini batch. That's because it adds noise to the model, and it regularizes the model kind of. For most of the applications, like imagine classification, it might overfit and you might need some noise to regularize your model. But some other applications, like for instance, imagine deep reinforcement learning, it might destabilize the training. So that's why they proposed a new model called weight normalization. This model, weight normalization, actually consists of two main parts. First part is somehow similar to batch normalization, and it tries to set the initial parameters in such a way that we get some benefits of scaling, almost the same as batch normalization. And most important part is reparameterizing the network weights in a way that it doesn't regularize the model and it doesn't add noise to the model. First, let's first start with the initialization of the model. I should also mention that for this model, unlike batch normalization, we have to initialize our network like in a proper way. But in batch normalization, it doesn't matter how you're initializing your network, because in every step it's going to normalize the values and nothing actually happens. But in this, maybe it's a drawback of this model that we should be a bit more careful about the initialization. So for that, let's first start with the initialization. We randomly initialize weights and bias for each unit, and then we do a single forward pass. And then for each unit, we compute pre-activation T before applying activation, as you can see here. Then we compute its mean and standard deviation, and we rescale our weights and bias, as you can see here. For that purpose, we divide weights by standard deviation, and we take our bias, we subtract the mean and divide it by standard deviation. So if we compute a pre-activation with respect to new parameters, we have something which is mean 0 and standard deviation 1. The same thing that we have in batch normalization. Now we apply activation function and feed it through neural network. As you can see, if we do the same thing for all hidden layers, then the model will be almost the same as batch normalization with slight differences. But in weight normalization, we just do it for the input layer, not for the all hidden layers. And the most important part of this model, which is unique, is reparameterization to speed up the convergence of this optimization procedure. They reparameterize each weight vector W with a parameter vector V and a scalar parameter G. And we perform stochastic gradient descent with respect to those parameters instead of the original parameters. So here, V is a k-dimensional vector, G is scalar, as I said, and then we divide it by the Euclidean norm of V. This reparameterization actually separates direction and length of weight vector, and it fixes the Euclidean norm of the weight vector. And as you see, so norm of weight vector equals G, the scalar, and it's independent of V, vector V. And the direction of the weight vector equals this one, V divided by the Euclidean norm of V. That's the direction. We actually separated those values. By separating the norm and the weight of a vector, we speed up convergence of stochastic gradient descent optimization, as we will see in the experiments. So here, with the help of stochastic gradient descent, we can train our model with new parameters, with respect to new parameters. So we need to compute the gradient of the loss function with respect to new parameters, as I said here. Actually, we do it separately for G and V. And the other one here is the same thing, just this is an alternative way of writing the same formula with the help of projection matrix. It might be a bit easier to implement with both the other formula. In this part, actually, weight normalization follows two main goals. First, it scales the weight gradients by this one, G divided by Euclidean norm of V. So it scales the weight by this one, and it projects the gradient away from the current vector. To consequently speed up the optimization process. But one of the interesting parts of this model is the vector V, actually. It can fix itself while optimization. Assume scale factor, which I already mentioned, this one, we call it scale factor. It means that meanwhile optimization, the length of V grows and the denominator of this deduction. It grows and the effective learning rate decreases. But well, the effect that has is that the model can automatically tune the learning rates. But that also matters how fast the norm of V grows. Well, it depends on two factors. If you take large steps, the norm of V increases quickly. On the other hand, if you are taking small steps, it stays almost the same. The fact is that we can combine weight normalization with batch normalization. I mean, instead of just normalizing the pre-activations for the first layer, we can do it for all the hidden layers as well. But here in this paper, they propose a better approach with less computational overhead, which is they named it batch mean batch only normalization. In this approach, we do subtract the mean from pre-activation, as you can see here, but we don't divide it by mini batches, by standard deviation of the mini batch. So this is a cheaper operation, and the computational overhead is lower than for batch normalization. And in addition, this method causes less noise during training. And we can actually calculate the loss function, this formula for batch normalization. And the model is, we can apply it on for many applications, and the result is almost the same as batch normalization. But the purpose of proposing this model in this paper is combining it with weight normalization. But we will see that they also investigated the results of this model without combining it with any other model. So as I said, then we can combine this approach, mean-only batch normalization with weight normalization. So as we can see in this approach, weights are scaled the same way we do it for weight normalization. Here, it's the same as weight normalization. Then we subtract the pre-activation from it, then feed it through the activation function. And the difference is then we do the same thing for all the hidden layers, not only for the input layer. That's the new approach, actually the combination of the weight normalization with something almost the same as batch normalization, but with slight changes for the to cause less computational overhead, and also adding less noise to our model. And for the experiments, I already said that this method is suitable for some applications like supervised classification, generative models, reinforcement learning, but it is actually a general solution which can be applied to train any network. In this paper, they only showed the results of applying the model on these specific applications. First, I start with supervised classification. They applied the model on CFAR10 supervised classification problem. CFAR10 dataset consists of 60,000 color images in 10 classes. These are 50,000 training images and 10,000 test images. And the dataset is divided into 5 training batch and 1 test batch, each with almost 10,000 images. And this is actually a comparison between batch normalization, weight normalization, normal parameterization, mean-only batch normalization, and finally a combination of mean-only batch normalization with weight normalization. So for all the models, they try to optimize the learning rates to reach the lowest possible training error after 100 epochs to find out how quickly they optimize. So as you can see, the batch normalization is still the quickest here, but other approaches like weight normalization, the normal parameterization, the mean-only batch normalization have almost similar test accuracy, almost 8.5% error. But batch normalization does better here at 8.05% error. But mean-only batch normalization combined with weight normalization has the best performance, 7.3% error, and does much better than mean-only batch normalization. As the final result, we figure out that weight normalization and normal parameterization obtain almost the same result as batch normalization. Maybe batch normalization is a little bit better, but not so much. But the interesting fact is mean only batch normalization combined with weight normalization outperforms supervised classification here. The second experiment is training a generative model and the effect of weight normalization applied to deep convolutional variational autoencoders. It is trained on MNIST dataset of images. This is a dataset of images of handwritten digits and also the CFAR10. And here CFAR10 contains small images of nature. It is a comparison between normal parameterization and weight normalization. They found that you get better results using weight normalization, and it is also more consistent because, as you can see, the error bars are much smaller for weight normalization, which means with weight normalization, we have lower variance and converges a better optimal. And actually, with less epochs, the model starts generating new images. And finally, the last experiment is on reinforcement learning. For that, they applied weight normalization to the problem of reinforcement learning for playing games on the Atari learning environment. The approach they used is the deep Q network. For the problem, batch normalization is not suitable because the noise produced in this model destabilized the learning process. So they compared weight normalization with normal parameterization here. And we can see that on average, the scores improved for weight normalization here. And as a conclusion, weight normalization is a reparameterization of weight vectors. This method accelerates the convergence of stochastic gradient descent. It might be a good alternative for batch normalization in some applications, and the reparameterization method is easy to apply and has a low computational overhead.